and they've torn apart, so there's no strong force holding them together anymore. But you do still have lots of protons here repelling lots of protons here. So that means that these two pieces, let me draw some arrows here. Okay, these two pieces are going to be repelled from each other, and they're going to fly apart really, really fast. Okay, so as we can see, some energy is released in this process, because before we just had one nucleus just sitting there. Now we have two big chunks which are flying apart away from each other really, really fast. And by really, really fast, I mean about 20% of the speed of light. These things go flying apart like they don't want to have anything to do with each other. So 20% the speed of light, that's a lot of energy that comes out. And we'll get into how much energy and try to put that into more, uh, well, more understandable terms in just a moment. Okay, so what we've seen is the krypton and the barium will fly apart and be carrying a lot of kinetic energy with them when they go. There's also 3 neutrons left over, which we're going to get to in just a moment. Now, I would just like to point out here, it doesn't have to be krypton and barium. There's nothing magical about krypton and barium. This uranium-236 nucleus can break into a large number of different chunks. You just kind of look at the middle of the periodic table, but it generally breaks into 2 pieces, and the total protons will add up to 92. But it doesn't have to be krypton and barium. It can be, for example, see, krypton and barium, krypton 36, and barium is, let's see, it was this one down here, 56. It could also be like xenon and strontium. If you add up 38 for strontium and 54 for xenon, you again get 92. You could also have yttrium and iodine. That's 2 other pieces that it could break into. So there's nothing magical about krypton and barium. That's just the 2 elements that I chose for this example. Okay. And when it does happen to be krypton and barium, you get 3 extra neutrons. If these are other elements like strontium and xenon, you'll have different number of neutrons left over. But the krypton, barium, and 3 neutrons is convenient for us, and we'll see why here in just a moment. Okay, so well, actually, this is a good time. The reason that we use this krypton and barium very commonly when we talk about chain reactions and nuclear reactions is because on average, we get 3 neutrons. So these can break into many different pieces, and depending on the pieces, you get different number of neutrons. But on average, we get about 3 neutrons. And it just turns out that krypton and barium is a pair that produces exactly 3 neutrons. So we use that because it's a good representation of what happens in general. Anyway, why do we care about these 3 neutrons? Okay, suppose that we have a bunch of uranium-235 nuclei all bunched together here. Okay, we've sorted them out, so we've pulled out all the uranium-235 from natural uranium, and we've made pretty much pure uranium-235. And one neutron comes sailing along and runs into one uranium-235 nucleus. Now, what we've seen is it will turn to uranium-236 and it will break itself apart. Okay, so that uranium-236 breaks into krypton and barium and releases a bunch of energy. And I don't have that in this diagram here because it clutters things up. What we're interested in is those 3 neutrons that also come out of that fission, that splitting of that atom. Okay, it turns out that each of those 3 neutrons can run into another uranium-235 nucleus. So when this neutron runs into this uranium-235 nucleus, it turns into uranium-236 and it breaks into krypton and barium and releases a bunch of energy. Same thing happens with this nucleus here. Same thing happens with this nucleus here. So we started off with 1 neutron fired into this lump of uranium-235, and after 1 step, now we have 3 neutrons and some energy. Well, what happens then? Those 3 new the 3 nuclei, each one of them breaks into pieces. Each one of them releases energy, and each one of them releases 3 more neutrons. So in the second generation, now we have 9 neutrons, and we can cause fission in 9 uranium-235 nuclei. Okay, and this can progress. This is why we call it a nuclear chain reaction. We have a chain of reactions from one neutron producing 3 neutrons, producing 9 neutrons, and on each step of the process, each link of the chain, we are releasing more and more energy. That's a nuclear chain reaction, and that's how we get energy out of this out of a nuclear chain reaction. Okay. And then those continue on, and we get more and more neutrons going out and multiplying the reaction. Okay, so what's the big deal? Why do we care about this? I've been saying and implying that there's a lot of energy here, but how much energy are we talking about? So I have to introduce another term here, which is called an electron volt in my neat handwriting, an electron volt, and the abbreviation for it is small e, big V, EV. EV. Now, again, you do not have to know, if you're taking notes here, you don't have to know what an electron volt is. I'm just introducing this term to put things in perspective. Okay, an electron volt is a very tiny amount of energy. Okay, so physicists measure energy in different ways, and electron volts is kind of the smallest unit of energy that we use. And we've chosen this very, very tiny unit of energy so that we can talk about individual reactions between individual atoms. We're talking chemical reactions here, and have a number that we can hang on that, which has some meaning. So, for example, as you know, if you combine hydrogen and oxygen, you make water. So if we take 2 hydrogen atoms, I mean 2 individual hydrogen atoms, and 1 atom of oxygen, so we're talking about a total of 3 atoms here, they will combine to make one single water molecule, and they will release some energy. They will release about 6 electron volts of energy. So this number, 6 electron volts, is something that we can hang on a reaction of individual atoms and be able to get our mind around it. Okay, so an electron volt is a tiny amount of energy. And it was created to talk about chemical reactions between individual atoms. Okay, so how much energy do we get when we split a uranium-235 nucleus from a nuclear reaction, not a chemical reaction? Well, they did the math on this, and they figured out that here it is. How many electron volts? It's not 200. It's not 200,000. It's 200 million. 200 million electron volts from a single nuclei of uranium-235 splitting. So compare 200 million to 6. We're talking 3 atoms here that produce 6 electron volts of energy. If we split 1 nucleus of a uranium atom, we get 200 million electron volts. And you can get out your calculator and figure out how many times more energy that is from a single atom. Now, this number really is too big for us to get our minds around. This is so much energy that if you had a single uranium atom do its fission thing on your hand, there's enough energy that you could feel it. There's enough energy to trigger a nerve impulse in one of your nerve endings. You'd be able to feel it like a little itch or a little spark on your finger. If you were looking at a grain of sand under a magnifying glass, you don't even need a powerful microscope. You can do this with just a strong magnifying glass, and 1 atom goes off underneath that grain of sand. You can see the grain of sand move from a single atom. Yes, enormous amounts of energy coming out of this. Again, it's kind of hard for us to get our minds around about how big that number is. But yeah, 200 million electron volts, that's a lot of energy. Okay, now what do we use nuclear chain reactions for? Well, it depends on whether we decide to make it a controlled or an uncontrolled reaction. If we do an uncontrolled reaction, in other words, and this diagram I showed you really is an uncontrolled reaction. These neutrons just go and hit more uranium-235, and there's a lot of uranium-235 around for them to hit. Nothing is going to slow this down. Nothing's going to stop this. This is an uncontrolled chain reaction, and you'll get a nuclear bomb out of it. Now, nuclear bombs aren't very good for powering our civilization. They're kind of bad for people. So we have found ways to control these chain reactions, and when we are able to control the reactions, basically control the rate of how often atoms undergo fission, then that's a nuclear power plant. If we can control the rate of energy release, then we can get energy from this. Now, how do we control a chain reaction? This is something I do want you to know. All right, so here's that same diagram here of the chain reaction happening. And these atoms have undergone fission. They've released a total of 9 neutrons, which are going to multiply the reaction. Now, what we use is control rods. And these are literally sticks that are made of either cadmium or boron, or they're soaked with cadmium or boron, but they're literally rods, sticks. They in the first nuclear reactors, they used wooden sticks wrapped in cloth that had been soaked in boron. And they still use metal rods now, which are made of cadmium or alloys of metal that have a lot of boron in them. Now, it turns out that cadmium and boron absorb neutrons. So when a neutron hits a cadmium nucleus, that cadmium nucleus just soaks it up, and it turns into an isotope of cadmium that has one more neutron in it. And it makes no difference. It's totally stable, just like carbon 12 was totally stable. If you shoot a neutron into a cadmium nucleus, it's still cadmium, it's still stable. It doesn't do anything. It doesn't do fission or explode or do anything like that. Same thing with boron. Boron can soak up lots of neutrons and still be boron. So if you take a rod of these materials and you drop it into your reactor so that it gets in the way of some of these neutrons, now these neutrons are soaked up by the control rod. They don't run into other uranium atoms, so they don't react and they don't release more energy. So by doing this, you have one uranium atom which released 3 neutrons, and those 3 neutrons ultimately make only one more. Well, actually, I've kind of done it this way. These 3 nuclei have released 9 neutrons. The control rods soak up 6 of those neutrons. So those 3 fissions result in 3 more fissions. So instead of 1 going to 3 and 3 going to 9, we have 3 reactions going to 3 reactions. That's a steady rate of uh, of energy release. This thing doesn't run away and explode like a bomb. It just sits there and produces heat like a fire or a pile of coals, putting out heat at a constant rate. Okay. Now, obviously, this is kind of a simplified thing because it appears that these neutrons are just going to be able to explode. Remember, these neutrons go off in random directions. So if you put enough control rods in the reactor, it will catch 2 out of 3 of the nuclei of the neutrons, and it will maintain a steady rate. If you find that the rate of reaction is increasing, the thing's heating up, well, you just lower the control rod farther into the reactor to catch a few more neutrons, and that slows down the reaction. If you find that the fire isn't going hot enough, and you want to get more energy out of it, then you lift the control rod out, and so you allow more neutrons to escape, and you allow the chain reaction to increase in rate. So that's literally how they do it. There's also kind of a fail-safe on nuclear reactors where they hold these control rods, they hold them up with electromagnets. So they put an electromagnet up at the top of this, and they use the electricity from the reactor to power the electromagnet that holds this control rod up out of the reactor. Now, what if there's a problem and like the electricity to the cooling pumps or something fails and there's no electricity going to this reactor anymore? Well, then the electromagnet turns off and the control rod drops all the way into the reactor and shuts down the reaction completely. Very simple design, works fairly well. Obviously, there's a lot more backups than that, but yeah, control rods are very, very important to controlling chain reactions.